Welcome to the second lecture in the lecture series on speed control of three-phase induction motor. In the previous lecture, we discussed about the stator voltage control method and the pole changing method for controlling the speed of three-phase induction motor. In this lecture, we'll talk about frequency control method, variable voltage variable frequency control or constant V by F method, and also rotor resistance control. So let's start with speed control by variation of supply frequency. As we already know, the synchronous speed of rotating magnetic field in the stator is given by the expression Ns is equals to 120 F by P. Hence, by changing the frequency of supply, the synchronous speed and hence the speed of the motor can be varied. Although this method of speed control appears to be very simple, but there is an inherent problem with this scheme. So now let's see what this problem is. The EMF induced in the stator of the induction motor is given by the equation E1 is equals to 4.44 kW1 F5 into N1. Here kW1 is the winding constant of the stator winding, N1 is the number of turns per phase in the stator winding, F is the stator supply frequency. So kW1 and N1 are constant and the equation simplifies to E1 is directly proportional to F into phi. If the stator voltage drop is further neglected, then the terminal voltage or stator supply voltage V1 is equals to E1. So we can write V1 is directly proportional to F into phi. In terms of flux, we can write flux phi is directly proportional to V1 by F. From this equation, we can see that the flux is inversely proportional to frequency if the supply voltage is constant. So if frequency is changed, the synchronous speed changes. But if frequency is decreased, keeping rated supply voltage, the air gap flux will increase, which will cause magnetic saturation of the stator and rotor cores. Again, if we increase frequency keeping rated supply voltage, the synchronous speed increases, but the flux in the core will reduce, which will cause reduced torque per ampere of current. This is the problem of frequency control method. If frequency is decreased, to decrease the speed of induction motor, the flux saturates, and if frequency is increased, to increase the speed of the induction motor, the flux reduces, which may cause reduced torque. So, in order to implement frequency control method, the flux in the core must be maintained constant. And this is only possible if voltage is changed in the same proportion as the frequency such that the flux density and the flux is constant. This particular method of speed control of induction motor is called constant V by F control or variable voltage variable frequency control. So from the equation V1 by F is directly proportional to phi, we can see that if flux decreases, if frequency decreases, flux will increase, but if at the same time the voltage is reduced in the same proportion, then for that flux will again decrease such that the net flux in the core remains constant. So basically what we are doing is that voltage and frequency are changed in the same proportion such that the ratio of V by F is maintained constant, which will ultimately lead to constant flux. As V by F is maintained constant in this method, hence the name comes constant V by F method. This is one of the most popular method for controlling the speed of an induction motor at subsynchronous speeds or speeds below synchronous speed. Now for supersynchronous speeds, if frequency is increased, frequency can be increased, but voltage cannot be increased in the same proportion as frequency, as because there are limitations of insulation. Frequency can be increased, but voltage cannot be increased above rated value, which may lead to deterioration or failure of insulation. So this method of speed control, that is constant VYF control method, provides a wide speed control range with a gradual variation of speed throughout the range. We have previously seen in pole changing method that speed control was only possible in steps in the ratio of 2:1. But in case of VYF control, a very smooth speed control over a wide range is possible, and hence it explains the popularity of this method. The next method is the rotor resistance control method. This method of speed control is only applicable for wound rotor induction motor because for this type of rotor construction, additional resistance can be added on the rotor side. We know the torque equation of a three-phase induction motor is given by the expression T is directly proportional to S into E2 square into R2 divided by R2 square plus S into X2 whole square. During the running of the induction motor, that is in slow slip region, or when the speed of the motor is very close to synchronous speed, the term S into X2 square will be very small as compared to R2, and so it can be neglected. Also E2, that is the standstill induced EMF in the rotor, is constant, so the equation can be simplified as torque T is directly proportional to S divided by R2. So for constant torque operation, slip is directly proportional to rotor resistance. If rotor resistance is increased, the slip will increase, which will further cause reduction in speed. Thus, by adding additional resistance in the rotor circuit, we can decrease the speed of three-phase induction motor. The main advantage of rotor resistance control is that the starting torque will get increased. But this method also has certain disadvantages, or also suffers from certain disadvantages. Firstly, speeds above normal speed cannot be achieved, or control of speeds above normal speeds is not possible because rotor resistance can only be added. Secondly, for wide variations of speed, a large value of external resistance is required, which will cause large copper losses and ultimately lead to reduction in efficiency. Also, this method of speed control cannot be used for squirrel cage induction motors because in the rotor construction of squirrel cage induction motor, there is no provision to add external resistances. And because of the addition of external resistances, I square R losses will increase. So in this lecture series on the topic of speed control of three-phase induction motor, we have learned about the different methods employed for the speed control, and I hope this was useful to all of you. Thank you.